So hi everyone. Today we're going to talk about BlueBorne. Thank you. So BlueBorne is a new attack vector we have discovered in the last year. It's an airborne attack vector because it's wireless. It uses Bluetooth. Today our talk specifically is going to be focused on Linux devices, on IoT Linux devices, and the vulnerabilities in Bluetooth that we found in the implementation in Linux. So, my name is Ben Seri. I'm the head of research at ARMIS, and today with me is...
I'm Greg. I am also a researcher at ARMIS.
And we both work in ARMIS, which is an IoT security company that is focused on the unmanaged devices in each corporate organization. Discovering these devices, profiling them, and sanctioning them. And for that reason, we came across researching Bluetooth to understand how some of these devices communicate. And through understanding Bluetooth, we found a magnitude of 8 vulnerabilities in different operating systems. So today, I'm going to talk a bit about other airborne attacks that have been discovered in the last year, wireless attacks, a bit of Bluetooth background that is necessary to understand the vulnerabilities and how they can be exploited. We're going to talk about specifically the Bluetooth stack in Linux, which is called Blues, and then a remote exploitation, how we did the remote exploitation of these vulnerabilities in the RC vulnerability we found in the Linux kernel. On 2 devices, we are going to show this on the Amazon Echo and the Samsung Gear smartwatch. And hopefully, if all goes well with the setup, we're going to do a live demo of this at the end of our talk as well. So in the last year, there have been a lot of research in wireless security, really groundbreaking research. And in Broadcom chips, 2 major research was done. One by Exodus, it's called BroadPon, and the other by Project Zero's researcher. Both found RC vulnerabilities in Broadcom Wi-Fi chips, which are already prevalent in a lot of devices, which allows you to take over devices over Wi-Fi, which use Broadcom in devices that use Broadcom chips. Another Wi-Fi research was Crack, is going to be here tomorrow, the researcher. You've probably heard of it. It's protocol flaws in Wi-Fi that enable attacker to either decrypt or even inject, in some cases, Wi-Fi packets in secure networks. And lastly, our own research, BlueBorne, was also found this year on Bluetooth vulnerabilities. So this is a field in which a lot of research is being done. And although we feel there have been previous research, it seems that more work is needed to secure wireless communications. So BlueBorne is an attack vector that targets a lot of devices that use Bluetooth, in which one of the 5 operating systems that we found vulnerabilities in. So it's Android, Windows, Linux, and iOS. And it's really a very powerful attack vector since it affected so many devices. 5.3 billion devices were at risk from these vulnerabilities. It is actually a subset of 8 vulnerabilities which affect each operating system a bit differently. And they are the most severe Bluetooth vulnerabilities that we know of to date. And this is because these vulnerabilities enable an attacker either to gain remote code execution, to get code execution on devices, to do man-in-the-middle attacks, so to inject or sniff packets, network packets without authentication, and information leak vulnerabilities that enable attacker either to bypass mitigations or just to leak crucial data from devices. The reason these vulnerabilities are so severe because they do not require any user interaction or any authentication. And an attacker can just bypass and attack a device remotely without anyone knowing that it happened. In the diagram here, you can just see the Bluetooth stack, or a part of a typical Bluetooth stack, and all the different 8 vulnerabilities that we found and where are in their location in the stack. And as you can see, the vulnerabilities are not in one specific area in the stack. They are actually all across the stack, each vulnerability affecting a different operating system. So either the RC vulnerabilities or the man-in-the-middle vulnerabilities or the information leak vulnerabilities, each are across the stack, and this is just a testament to the fact that no specific part is vulnerable, but the general feeling that the Bluetooth implementations have not been audited enough, and so for that reason we found so many vulnerabilities. And now Greg is going to talk about discoverability, which is a main concept in Bluetooth, and it is the first step that is needed for an attacker to bypass in order to attack Bluetooth devices.
Okay. So there is a common misconception in Bluetooth that two devices, in order to communicate, need to pair with each other. And in the case in the general case of normal devices, that is true. When they don't know each other yet, during this pairing they exchange identifiers, the main of which is their Bluetooth address. It's just a MAC address, it's a 6-byte address. However, once a device or an attacker knows these 6 bytes, this address, he or she can communicate with that device even when it's not discoverable. So on most operating systems, Bluetooth devices are always listening to incoming connections. They're not always discoverable, but they're always listening for incoming connections, almost in all cases, when Bluetooth is turned on. And it is turned on by default on most machines that have Bluetooth hardware. So again, a device does not need to be discoverable in order for an attacker to use Bluetooth as a vector. In addition to this MAC identifying a device, it's also part of it, a significant part of it, is also transmitted plain text over the air in every Bluetooth packet. So that means if two devices are communicated via Bluetooth, an attacker that is nearby and can sniff the radio can get basically 80% of that address out of the air from a single packet, and then brute force the rest, which is on 32 options or so, and is able to communicate with one of the devices. Now this isn't new. Open source tools, hardware tools have existed for a long time doing this. Here we're showing the Ubertooth tool. It costs about $100. It's been available for some years now. And basically what it does is that an attacker puts it on some Bluetooth channel, and it's just listening for packets from any device to any device and picks them up. And basically it shows the addresses of communicating devices in the air, even when they're not discoverable. The only thing they need to do is to actually communicate. Now this was a hardware solution that cost $100. Purely software solutions do exist for that. It's possible to modify the firmware of existing Bluetooth adapters or Bluetooth chips. It's pretty difficult, but work on this has been done in the past, and we've seen examples that do that. We actually found something both cheaper and simpler, a sub $1 solution, if you will. And this is using this NRF24 chipset or module that you can buy on Alibaba for less than $1. It's based on this NRF24 chipset, which is used for wireless keyboards and mice, which actually the Microsoft and Logitech and a few other companies, they don't use Bluetooth for their keyboards and mice. They use something that's called a proprietary protocol over 2.4 gigahertz, which just so happens to be on the same channels, frequencies, and modulated exactly the same as Bluetooth, but it's not Bluetooth. So we found a trick, simply to configure this device in a way that will sniff Bluetooth. And additionally, there has been research done in the past of how to promiscuously sniff MACs of keyboards and mice from these adapters by a researcher called Travis Goodspeed. You might have heard of him. So we combined these two tricks in order to get basically the same functionality as the Ubertooth and be able to sniff out Bluetooth addresses from the air. The code for this is on our GitHub. It's a Python script.
No, just after the talk, it's going to be on the GitHub.
Okay, fine. Okay. Now, in addition to the things I've shown before, it's also pretty common for equipment manufacturers, OEMs, to set either the same or adjacent MAC addresses to the Wi-Fi and Bluetooth chipset. So basically, lots of existing hardware is on the market that can sniff Wi-Fi in monitor mode. So if you just sniff Wi-Fi packets of a device and it has Bluetooth enabled, and it's one of the majority, I suppose, of devices where the Bluetooth address is adjacent, then you also know the Bluetooth address, basically. So that's also a way. And even a step further, if the attacker is both in proximity physically and on the same network, then they can know the MAC address, the Wi-Fi MAC address and the Bluetooth address, just from looking at its ARP cache. Okay, so now we can communicate with the Bluetooth device. How do we attack it? Bluetooth has a very large attack surface. What you see here, the boxes above are the profiles and services of Bluetooth. These are the higher level things that you know of, like Ethernet tethering or sound or stuff like that, HID. There are lots of those. One of them is called SDP. It's the Service Discovery Protocol. It's a protocol that allows you to discover what other protocols are available on the device. Below that is the L2 cap layer. The L2 cap layer is basically the transport layer, the reliable transport layer. It's like TCP for Bluetooth in many ways. And below that are the hardware communication with the Bluetooth adapter and the packet layers, ACL and such. A lot of these services, they do not require authentication to connect. For instance, SDP, obviously by design. And except for that huge attack surface, it's all extremely complicated. The spec that defines most of this stuff that you see here is very long. Some pages look like this one. And this one particularly, what it shows is what's called packet fragmentation that's implemented in 4 different layers up to and including L2 cap. Why would you need that? I don't know, but it exists. Now, every time packet fragmentation is something that's pretty bug prone in implementations. So every implementation has 4 chances of getting it wrong, and they do. And now in this talk, we're going to talk about the Blues implementation, which is the Linux implementation of Bluetooth. It's been around since 2001, and you may note that Bluetooth has been around from 1998. It's actually the first native OS Bluetooth stack that exists inside Linux. And what it does is talk to Bluetooth controllers, to the hardware devices. It has a kernel-side implementation of the lower protocols. The HCI is the communication with the hardware, ACL is the packet protocol, and L2 cap is the TCP transport protocol. Besides that, there is a user-land implementation in a daemon called BluetoothD. It does pairing and authentication, the higher-level stuff. It provides those services, including SDP, and it runs as root. So interestingly, all this huge attack surface, all of it runs at least as root, and some of it in kernel. And now Ben is going to talk to you particularly about a vulnerability that we found in the L2 cap layer in Linux.
Yes. So as Greg was saying, L2 cap is the Bluetooth equivalent of TCP. It is a transport layer. So it is like TCP. It does connection. It does the connection to the servers, to the services, and it offers some quality of service features. So you can have a reliable connection over the non-reliable ACL packets. So basically, like TCP, you can have your service listening for incoming connections, and you have a Bluetooth client connecting to it, and L2 cap will be that transport layer that will allow that connection to take place. Since it offers a lot of quality of surface features, there is a lot of code to implement those features, so there's a wide attack surface in L2 cap. And as Greg mentioned before, L2 cap in Blues specifically is implemented inside the kernel, so vulnerability there might be very vulnerable, very good to an attacker. So there is a concept in L2 cap that's called mutual configuration. It helps do the quality of service negotiation in the start of the connection. The connection parameters are negotiated in this process. And the way it works is that device A in this diagram will send a configuration request message, which will basically have plenty of options, plenty of configuration elements in it, like the MTU of the connection, like what quality of service features you want to implement in that connection, and so on. And he will send that message to device B. Device B will then either accept that configuration or reject it with a configuration response message. And if he chooses to reject it, he can offer an alternative configuration parameters. So he can change the MTU or other connection parameters and send them in the configuration response message. If he rejects them, device A will then offer another configuration with another configuration request and so on, and they will negotiate until they reach an agreement on the parameters. In this process, it's called mutual configuration because it happens in both ways. So each device will negotiate its sides of the connection parameters, sending the configuration request, and the same will happen vice versa on the other end. So here we can see an example of this process. Device A on the left will send the configuration request with a number of options in the message of the correct configuration parameters. And device B on the right will send a configuration response. In this instance, the result is failure, so he unaccepted the parameters, and he offered to change some parameter in some way. Like I said before, in device A, when he receives this configuration response message, he will then need to build another configuration request message and continue the negotiation process. And this is exactly the mechanism, the negotiation process here, in which we found the RC vulnerability in the kernel. So this function parses the configuration response, so the messages that are being returned to the configuration request. And then it needs to build an output configuration request message that will be returned, so the negotiation process will continue. And looking at the prototype of the function, we noticed that something is missing. The highlighted arguments there, or the RSP variable, is the input configuration response message pointer. The len is that length of that message. And then data pointer is the out parameter. It's the configuration request message that will be built in the process of parsing this input message and returned to the other peer. And the data argument doesn't have a length attached to it. So this function doesn't know what are the bounds, what is the size of this data pointer, and it just copies the input configuration elements from one end, from the response message to the new request message that is being built, and there is no validation of the bounds of this memory pointer, of the data pointer here. In the while loop there, it just goes and gets all the configuration elements from the message, from the input message, and copies them or changes them depending on their data into the data pointer that is pointed with PTR over there. So this function, this L2CAP parse conf RSP function, is vulnerable. It can write out of bounds to the data pointer that it receives. What is that pointer? So in this context, it is the buff pointer that is being passed to it. This function is the function that receives the configuration response messages. So buff here is just a 64-byte buffer on the stack. So obviously a stack overflow can be abused in this flow. The only caveat here is that the device needs to be in the pending state, which actually is a state that the attacker has a lot of control over. So prior to sending this overflow message, he can send another message that will put the device in the pending state, and then the overflow can be triggered. So what is the strategy for this exploit? It is a classic stack overflow like the 90s, like the good old days, so it shouldn't be too hard, but there are some limitations. We need the ability to send whatever configuration response messages we'd like, because it is not usually that the way it works. So usually you have your stack and it will do the negotiation, it will send whatever configuration response messages it like. So we developed a small testing framework for us to send raw configuration response messages. We're going to do a stack overflow, but want to know what are we going to overflow. We want to choose our overflow very specifically, so we need to find either pointers or the return address of the function to overflow. And simultaneously, the buffer that we are going to use to overflow also needs to be a valid configuration response message, because in the loop here, in the while loop here, if we send an invalid configuration configuration element, the while loop would break and our overflow would stop. So it also has to be a valid response message. If there are any mitigations in the device that we are attacking, we need to bypass them before we trigger the overflow, either KSLR or stack canaries. And once we do the overflow, what we want is to develop a write-word primitive. So we have a control to write some data in some address in the memory. And that would allow us either to insert a warp chain or do a simple shell code that will be run inside the kernel once we have that primitive. We want a way to get out of the kernel to user space. That would be simpler to do post-exploitation. So we're going to use user mode helpers, which we're going to talk about later, to do that process. And lastly, if there are any LSM modules, Linux security modules like SELinux or others, we want to disable them before going to user space, because we are in kernel, we have that ability, so it would be nice to do that. So what are the expected mitigations in 2017 in any Linux device? What we expect to find in devices. ASLR is address space randomization. It would be hard for an attacker to know the addresses which you need to do the stack overflow, so that is to be expected. Stack canaries are very basic, very good mitigation to prevent stack overflows. Fortify source is a feature for even hardening stack canaries even more. So to put the stack buffers adjacent to the canaries, so if an attacker were to overflow that buffer, it would go into the canary, and he has to know with the canary to exploit this. And NXBit is a very basic feature in a lot of devices that is used to prevent data from being executed and code from being writable. So the attacker cannot simply jump to its shellcode either on the stack or in a different part in the memory. What are the real-world kernel configurations that we actually find? KSLR, the ASLR of the kernel, is not really enabled in any devices. It was only added to the default configuration of the kernel in very recent versions. And it is a hassle for a lot of devices to use it. So it's actually not being enabled at all. At least in devices that have Bluetooth, that's the case. Stack canaries are only enabled in the major Linux distributions. They are not in the default configuration of the kernel for some reason. So any device that uses mainline kernel just with the default configuration will not necessarily enable them. We actually haven't been able to find any IoT devices that use stack canaries, although they are very basic mitigation. There is the funny case of Fortify source being enabled, but stack canary is disabled. This is not a good combination, because if you have enabled Fortify source, the stack buffers will be placed on the bottom of the stack, and then the first overflow will be of the frame pointer or the return address, so you instantly have control over something that is significant. And this is actually the case of the Samsung smartwatch that we have exploited. No NXBit. We were really surprised to find out that the Amazon Echo does not use the NXBit or uses it poorly. We're not really sure. So we can do it like the 90s. We can just jump to our shellcode in the stack. So we have tested two devices for this RC vulnerability. One is the Samsung smartwatch. It runs a pretty new kernel, not that old, the kernel 3.18. It runs an ARM processor, 64-bit. It has very few mitigations, no KSLR, no stack canaries. It has a funny combination of Fortify source enabled, stack canaries disabled. It also has SMAC, which is in some alternative to SELinux, but we can bypass that once we have code execution in the kernel. And the second case study is the Amazon Echo, which is based on a very old kernel for some reason. It's 2.6 kernel. It runs on ARM 32-bit, and it has virtually no mitigations at all. No KSLR, no stack canaries, no Fortify source, no NXBit, no access control. In that case, there is no Fortify source, but it actually works in our benefit. We're going to show that because we can overflow something that is not the stack pointer or the frame pointer, and the fact is that there's a very, very nice and valuable pointer for the attacker that is pretty adjacent to the overflown buffer. Amazon has provided a patch for this just 2 weeks ago. So now Greg is going to talk about the limited RC flow we have in the old kernel that's run on the Echo.
Okay, so initially when we looked at the Echo and we've seen that it has such an old kernel, we actually didn't find that vulnerability that Ben has shown previously in this version because it existed in its form from Linux 3.3 and up. However, what we did find is that it does exist from kernel 2.6.32 and up in a more limited scenario. As you can see, the state that that case needs to be in there is unaccept in this case. Previously, it was in the pending state. Again, doesn't really matter. This is attacker controlled, more or less. However, the limitation here is this if above there. And what it does is it checks that the size of the input configuration response message is 60 bytes. And if you remember, the buffer we're overflowing is 64 bytes. So that should be a problem, right? Well, it turns out that it really isn't. What happens is that the configuration parameters come in elements, and these elements are built like TLVs, tag length value structures. So basically, there is 1 byte for type. In this case, type number 4 is that case down there called conf RFC. And the length can be 0, for example, so only 2 bytes are required to define a single element. But what this function does, this code is out of the same function that has the vulnerability, the original vulnerability in it. What this does is that the loop goes over all the input elements, and then it does something with them, and it writes out elements into the output. However, in this case, as you can see, the element that is written out is not of the 0 size that we've set, but of the actual real size for that element, which is that size of down there, which happens to be more than just these 2 bytes. So this means we can amplify the size of our elements inside the output buffer. And what we are showing here, this is actually the actual stack frame from the Echo on the previous version before it's patched. On the left there is our 2 byte, what we call the 0-len RFC element. And on the right, what's written to the stack frame, what's written to the output buffer is an 11-byte element because it's supposed to be 11 bytes long. So for every 2 bytes, we can write 11 bytes. And if we do the math, it shows that for the 60 bytes that we can input, we get 330 bytes of output, which is a lot more than 64 bytes that we should have had. One thing that is uncomfortable here is that the data is uncontrolled. This is uninitialized, what it's writing there in that element. Okay, so we looked at the stack frame itself on the Echo. And as Ben said, it has no 45 source, and therefore it is not adjacent to the return address or the saved registers. However, there's something more interesting there. The buffer is slightly above on the stack from a pointer called PTR, which you can see here. This is actually the pointer of where the next element is written to. So an element is parsed, pointer is updated to the next element in the output buffer. So if we overflow that with an element and we control what was written, then we control where the next element will be written. This gives us our write what where primitive. This is sort of what we want to do. However, there is an annoying limitation. Simply writing those 24 0-length RFCs will not allow us to control the pointer. It will overflow it, but the data will be uncontrolled. So we need to massage it in some way to find a solution to that. So basically, there are other elements except for RFC. They have different sizes. In this case, it's the flash and MTU elements. So we build our input buffer in such a way that what happens is that there are 22 empty RFCs that will bring us further away on the stack frame. And then we use other elements, in this case flash elements, to align ourselves to our write. And lastly, we can write 2 controlled bytes anywhere we want there. Well, basically where we align it to. The place we align it on is onto this pointer. This pointer again controls where the next element will be written to. And particularly here, we overflow the first 2 bytes of that pointer, and this is a little endian R machine. The first 2 bytes are the 2 least significant bytes of the address. This pointer is an address to the stack, so overflowing the 2 least significant bytes of an address on the stack lets us then write anywhere basically on the stack. And this is what we do. What you can see here is that at first we send all our elements that overflow PTR, and we write the 2 least significant bytes of where the next element will be written. And on the right, you see where we write those bytes, and we overflow the LR register on the save register, which is the return address of the function. We overflow 2 bytes here because that's kind of our limitation. And we can do that with a single L2cap conf response command. So it's kind of a problem writing just 2 bytes, but it turns out that Bluetooth being so complicated is good for us, again. Basically, it's possible in L2cap to put multiple commands into one packet. And in addition to that, there is a fragmentation layer below L2cap on ACL, which allows us to now build really large L2cap packets. So basically, we can pack together lots and lots of these commands, and then in a single packet write however many bytes we want on the stack. So what we'll do with that is at first write a shellcode somewhere on the stack. Again, there is no NX bit on this device, so we can just write a shellcode. And then overflow with 2 times 2 bytes the return address. There is a small caveat here. You may see that there are uncontrolled 2 bytes written in addition to our controlled 2 bytes, so we need to write them in reverse. Not a problem. And then our shellcode will be executed. As you can see here, if you can see, on the left there is that huge packet. It contains many, it's over ACL fragmentation, it's pretty large, and it contains many L2cap commands, which are the configure responses. And on the right is a particular single configuration response that has many of these empty RFC elements. These are the empty options that you see there, Wireshark and parsing. And lastly, there are the 2 flash elements that are used to actually write data. Okay, so now Ben is going to explain what you actually do with this as post-exploitation.
Yes. So as we said, we now have a kernel mode code execution, but we want something more convenient for us. We want to have a root shell. And for that, we use a very nice concept that exists inside the Linux kernel, which is called user mode helpers. It actually exists inside the kernel to allow it to run some commands in user space in different scenarios. For example, if a device wants to power off, he wants to do that gracefully, so he wants to run some power off commands in user space to shut down the services nicely before actually powering off the machine. So the orderly power function does exactly that, and it takes the power off command, which is a global, which is a writable string inside the kernel, and runs that command in user space. It also eventually powers off the machine, but it has a flag that allows you to prevent it from doing that. So our shellcode will basically write over that power off command whatever commands we want to run in user space and call the orderly power off function. So it's very simple. So just to recap on the exploit process, what we do is we begin an L2cap connection with a high MTU that will allow us to send the large packet that Greg showed you before, containing all of these multiple configuration response commands. They will write our shellcode to the stack in an unused area on the stack, and then also override the return address of the function, so our code will run. The payload will simply write whatever commands we want to run in user space on the power of command, execute the orderly power function, and finally it will restore execution, and the device will be unharmed, so it will continue to run. In the smartwatch, we had to have a different exploit, a bit for different exploit. It uses the same principles, but it does have to do something a bit different. The exploit was developed by a coworker of ours, Alon Livne, and it has to bypass the NX bit limitation, so the stack cannot be executed in this case, but we can do a basic warp chain that gives us the write port where primitive, and then we just do the same thing. We write our power off command with whatever command we want, and then run the orderly power off function, and that's it. That's it. Okay, so we wanted to take a look at devices that do have mitigations, unlike these specific devices that have stack canaries or KSLR. And this is like really, really new. We found this a week ago, and it's actually it's a new vulnerability that we found. It's the 9th Bluetooth vulnerability. So it's an information leak vulnerability from the Linux kernel in the same beloved function as conf RSP. So this information leak can allow attackers to bypass mitigations such as KSLR or stack canaries by leaking pointers or by leaking the stack canaries via Bluetooth connection. So what we can see here is the EFS variable is uninitialized on the stack, and there is a flow in the code that allows us to send it back to the attacker uninitialized, in its uninitialized state. The OLEN, you can see there is the input configuration element that is being parsed, so the attacker has the control of this length. So it can avoid the memcopy call by sending an EFS element which is not the size of EFS. And then the memcopy will not occur, but still the EFS variable will be returned to the attacker in the addconf opt function. So this is 16 bytes from the stack, uninitialized, and they will have somewhat of a random value, but the attacker can control what value would be on that uninitialized stack by doing prior calls to other functions before calling this function. So you can analyze the stack of this device is targeting, and you can make sure that in that uninitialized space, the stack canary or other pointers will be placed. So that way he can leak those, that data. And here we can see an example of this being done specifically on the smartwatch when we send the configuration response messages that will cause the return of configuration request with the EFS variable with its uninitialized stack variable. And those last 8 bytes in that hex dump is actually a pointer from the stack. It's a pointer of the code in that watch. Okay, so we're really close to an end here. We're going to do the demo in a second. I wanted to just recap on our takeaways from this presentation. Bluetooth implementations are really complex. This is like number one. I think we said that a bunch of times, and it's true. There was a lot of code, and what we found is that it is not examined enough. There are a lot of potential vulnerabilities still there, and this should be rethought and be audited. Mitigations in electronic devices are not actually always implemented. In IoT, this is a very extreme case, but I think that's also true for other devices. So unlike PCs, Linux devices sometimes do not use all the mitigations. And this needs to be fixed. There was no reason for the default kernel configuration to be so light on mitigations. And lastly, what we also think that should be taken from this is that no security mechanisms today actually are looking at Bluetooth communications or other not Wi-Fi wireless protocols. So any attack that will be taking place on these protocols will be completely under the radar for these mechanisms. So the new solutions need to be put in place to monitor these potentially vulnerable protocols as well. Okay, so we also have going to upload just now after the talk the exploit codes for both the Echo and the Gear, the white paper on the exploits, and there was also the previous technical white paper we already published that covers all the vulnerabilities in BlueBorne. Okay, so we're going to attempt to do a demo just now. I hope that works. It basically will going to start with one of the echoes. I'm not sure which, but we're going to see in a minute. So we're going to establish the Bluetooth connection to it, and then once we run our shell code and we do a connect back shell just over the Wi-Fi here. So once the attack is finished, Bluetooth is no longer needed, and just over the internet, this device can be controlled remotely. So I hope you can see there. So on the left, it's going to run the exploit script. I'm holding my fingers. You should do that too. So it sends a bunch of these commands, and now we have a shell.
Yeah.
So we upload some scripts to run on the Echo, and we can see that we are running in root. This is the configuration of the Bluetooth on the specific Amazon Echo. And we can do a bunch of things with it. Of course, it's a Linux device. We can control its LED. Here it goes. Now it's green.
If anyone can see that.
Yeah. Okay. It's a digital assistant, so we can make it say things. Also, it's just for fun. So I can say, Alexa. Alexa.
My name is Alexa. I have been owned. Take me to your leader.
Okay, I will try to take you to your leader. And now we can also take this attack a step further. So what if we want to create some of a botnet of Bluetooth controlled or BlueBorne controlled devices? We can take over the Bluetooth connect device controller of this Amazon Echo and use it to attack another Amazon Echo, the next one over there, and then connect them all to our botnet of controlled devices. So the first one will connect back, and then the next one will connect back via the internet, and so forth. And each device can then attack another one. So we just created this for our fun, but this is just the hell scenario for this kind of attack. See, this is really just something pretty new, and I'm not sure it's going to work, but we're going to attempt it. So on the right, we can see the connect back shell for the second device, if it will actually connect. Okay, so it has. So now we have control of the second Echo on the right. On the left, it's the first Echo. So we have uploaded our scripts to it as well. We can see this is a different device. It has a different MAC address. We can also make it with Christmas lights. Here it goes. And they will all together sing our Christmas carol. Alexa.
My name is Alexa. I have been owned. Take me to your leader.
And just to wrap it up, we can also attack the gear, the Samsung gear. It's pretty small, and I don't think we can actually see it from the back, but it's over here. So the second, actually, it's supposed to be here, because the second Echo will then attack the gear as well. And like I said, each one of them, once we run the exploit, connects back via Wi-Fi to Greg's laptop over here. So they don't have really to be over here once they are controlled. So anybody can just attack one device, and that device can go around attacking other device, and all of them connect back to the botnet. So on the right is another shell. Okay. So, okay, 2 out of 3, but
we can try again.
We can try again.
But you need to restart it.
Actually, that's a pawnlib bug. As you can see, what Greg is trying to show is that this device has the Wi-Fi MAC address that are adjacent. So to find the MAC address is pretty simple. Just by pinging the IP of the device, we can have its MAC address in the ARP cache. So that's the 24920E. That one. That's the MAC address of the Wi-Fi. And the Bluetooth, there's actually just one adjacent to it. So let's try again and tag it. I hope that works. No, but
Of course.
oh yes. Okay, so we don't have any LEDs here or any audio, so you need to trust me, this is actually being pawned right now. But we can reboot it just to show it controlled without my hands. Does it reboot? Okay. Okay, I think we have time for Q&A if anyone wants to ask anything. Okay, yeah.
Hello, thank you for a really good talk. I just wanted to ask if there is any CVE assigned already for those vulnerabilities, and if it's being fixed, if it's already fixed in the most recent kernel version.
So the RC vulnerability is already fixed in September. This new vulnerability, the information leak, is actually just being fixed today. There was a CVE, and it's also going to be published on our website, so it's really new, the information leak one.
Hi, great presentation. I have a question about Android devices where the stack is pushed a lot into user space, and what your guys' thoughts are on that, and if you guys have any research.
So we did, of course, the exploitation in Android as well for the BlueBorne vulnerabilities. It does have a better, it doesn't run as root in Android devices, but it also has a lot of privileges. The Bluetooth stack in any device, but on Android as well, has a lot of features it needs to implement. So you have file sharing, and you have the ability to connect a mouse or a keyboard via Bluetooth. So all of these features have privileges inside a stack. So for one example, we just showed on Android the ability to connect a mouse or a keyboard, and then you can actually control the UI. That's one avenue to go. But there are also the file. You have a lot of access to the file system. So you do need another step to get to root in Android, but the attack surface is very, very wide since you have a lot of privileges there as well. So doing basic, I don't know, just getting the images of the phone or something, that's like from the start, that's privileges that you have. But to root it, actually, you need to do another step.
Yeah, and just to clarify, it's a different vulnerability on Android. It's not in the AutoCap layer, it's in a different point on the protocol stack. However, it's still a privileged process, not root, but still privileged enough to do lots of damage. Anyone else? Okay.
Hi. Hello. So thanks for a great talk, first off. I'd like to talk some more after the talk because I've got a lot of more questions that I can't answer right now. I do a lot of industrial control systems. I'm the author behind the horror scenario, the attack on the power grid via solar panels. And those things work either over Ethernet or over Bluetooth. Do you have any idea whether this will work on those devices?
Well, if they are based on Linux, if they are running Linux and using the native Bluetooth stack, Blues, yes, this will affect them. As I said in the start, there are 8 vulnerabilities we found, and they affect the Android, Windows, iOS, and Linux stacks. So, but there are other stacks other than these, not such widespread, but industrial devices might have proprietary stacks. I'm not sure, but if they are based on one of these systems, they will be affected. Other than that, like I said, the overall feeling is that all implementations can be affected by similar vulnerabilities because the stacks have not been audited in quite a long time.
Thank
Yeah, and what does affect every device that uses Bluetooth is the complexity of the Bluetooth protocol. Yeah, so every stack can be vulnerable because it's pretty complicated. However, you should also know that there is a difference between a full Bluetooth stack and a stack that only does Bluetooth low energy. It's a pretty different protocol from the ground up, and it has less features and thus is more secure. So if your device has only Bluetooth low energy, it's probably okay.
Probably.
Yeah. Anyone? No.
Okay, so you guys have got a limited window to explore the undocumented communication between the Echo and the mothership, which a lot of people would like to understand. Because it's locked down to an Amazon certificate, people can't just kind of put a Wireshark interceptor or anything in there. But with your exploit, you could actually do that. Have you got any plans to kind of look at that area?
Can you get me on the last part of the question?
Well, because all the communication that the Echo makes back to Amazon is over SSL, and it uses a cert that's signed by Amazon, so you can't just basically kind of intercept that traffic. But you guys could, now that you've got root on that device, you could use that to figure it out. A lot of people would like to know how that works.
So we are going to release the exploit, so you're welcome to take that and do with it whatever. But you should note that Amazon Echo receives automatic updates, and it's all being updated. I think that probably you can just buy a new Echo that hasn't been updated yet, and then you can use this to get root in order to research it further.
Yeah, well, this vuln for which the exploit that is going to be on our GitHub will work on the previous version of the Echo, the previous software version. So if you can somehow revert that, or you'll get root on your Echo.
So can I ask your suggestion for preventing further problems like this from Bluetooth implementation? I mean, for example, we can make a better implementation for Bluetooth stacks, or like on the presentation, adding some kind of a special secure mechanism, the monitoring mechanism on the Bluetooth stacks, like on Bluetooth stack on like a specific SE Linux for Bluetooth, the silly name, but for example. So what is your suggestion?
Yeah, go ahead.
Okay. Basically, there are two things. First of which is just use BLE unless you need the full Bluetooth. Second, it's the concept of lowest privilege. Okay, say it showed really well on Android and here on Linux as well. But on Android, there is a single daemon that has all the privileges of everything Bluetooth does. So the same daemon can be an HID keyboard. It can look at your pictures. It can do like attach network interfaces, crazy stuff, right? But there is no reason that a vulnerability on only one of these things will allow you to control all of these privileges. So it shouldn't be one daemon. It shouldn't be in the kernel. It should be many separated, low-privileged processes that do only their particular thing.
I think I would add to that is that we're very accustomed to the concept of firewalls in TCP connections, in IP connections, but there are no such firewalls in Bluetooth connections. So the services are always listening, and there is no way to stop them from listening or to limit their connections. And also, I think solutions that are looking at the protocol on the side, just analyzing the data, can also find very valuable and can also potentially block threats from not inside your device, but outside of the device as well.
Quick questions, please. Would you say that the way you built your exploit would affect all CPU architectures equally?
Excuse me, can you
CPU architectures, yeah. I think each exploit usually needs to be adjusted, adapted a little bit. It won't be automatically. Even the Amazon Echo, if you go to a different firmware version, you need to adjust some of the variables. But our job was not to make this a weaponized, nation-grade exploit, although sometimes we dream of that. But more like to show a proof concept of that. So any actor that wishes to take advantage of these vulnerabilities in the highest manner, he can do that. He can make the exploit generic or just customize it to a very wide variety of devices.
Thank you. So essentially you're saying it's possible, it just needs to be customized.
Yeah.
And the second question, you mentioned monitoring. Would you have any suggestion how you monitor mobile devices at all times?
I don't think I understand. You mean?
So your phone is essentially a mobile device. You carry it around. How would you monitor that?
So there is a number of ways. There is the way that you probably think about it, just spread hardware around the organization that monitors Wi-Fi and Bluetooth. Such things exist for Wi-Fi. I think they're called the wireless APS, right? Suppose they do kind of this thing. So if you monitor all these protocols that your device is exposed to the air, then you'll have at least a window into seeing what's actually going on and be able to control.
Yeah, but our company also does this specifically, monitors Bluetooth communications as well, either via specific hardware that we deploy or with some integration to existing infrastructure in your organization.
Hi, thank you very much. Absolutely fascinating presentation. I don't suppose I can ask a favour. Would you be able to put the URLs for your white paper back up, because I didn't get them down in time?
Okay.
Which one?
That's a little bit.
Ryan Shalat? Oh, sure.
Yeah. Also here, there was also a white paper and a presentation video in another venue we went to about Android. A white paper also exists there. If you go to our GitHub, you'll find all of this there tomorrow or so.
Yeah. Oh, you need a half an hour.
It's not up there. It's still got the black hat background.
Well, come to us later. And
Okay.
Anyone else? Thank you
So
very much.
thank you very much.